To continue our discussion about the forces on charged particles and magnetic fields, let's look at a collection of a whole lot of charged particles in a magnetic field, or in other words, a current in a magnetic field. So imagine I have this wire here, the black cylinder, and there's a current traveling from right to left, and furthermore, let's put it in a magnetic field facing into the page. A current, of course, is nothing more than a collection of charged particles moving in a wire. They're really electrons, but we can pretend, of course, that they're so-called charge carriers. So let's imagine it's a batch of little positive particles moving in the same direction as the current was, which was initially to the right. So each of these charged particles has a well-established drift speed as it goes through the wire, and if I just figure out how long it takes for it to go a section L of the wire, so let's say this is length L, then the time it's going to take to go length L is of course going to be that distance L divided by the drift speed. Furthermore, I can also say that the current in the wire, of course, is going to be charge per unit time, so Q over T. And I can rearrange the initial magnetic force equation I had, where the magnetic force equals QV cross B, by making a couple of substitutions. So instead of Q, I'm going to substitute in I times T. So my magnetic force is current times time times V cross B. Next substitution is I'm just going to replace my time T with L over the drift speed. And what I can now do is just sort of kill the magnitude of the velocity, but keep the direction and associate the direction of the velocity with the direction of, well, in this case it's a wire element, but in reality it's really sort of the current direction. So my magnetic force on a current carrying wire is going to have the magnitude current times that length of the wire that's in the magnetic field cross product the magnetic field. To find the direction, of course, you're going to use the right-hand rule. I could do it just on an individual charge carrier, but it's easier just to think about the direction of the wire as being the direction of the current. So let's say L hat is this way, and then using my right hand, point my right fingers in the direction of L, curl my right fingers into the page, and then I find thumbs up, the force on the wire is pointing upwards. So I've got a levitating wire. Okay, levitating wires are all well and good, but if you really want to have fun with this idea, you should introduce the idea of a railgun. You guys probably remember from Regents that if you have a current traveling in a wire, it produces a magnetic field of its own, which was a factor we were ignoring a little bit earlier, but it really has a lot to do here. So what a railgun is two rails, well, hence the name, and a conducting projectile that fits snugly between the rails. So if you turn on the current, it's going to go up one rail through the conducting projectile and out the other rail. So this is the path of the current, or lowercase I in this particular example. As I said, you should remember from Regents that any current carrying wire has a magnetic field created from that current circling around the wire. So these blue lines you see over here are showing the direction of the magnetic field around this wire. So what you're going to notice is that in between the two rails, the magnetic field is pointing more or less straight up. I don't know why I'm saying more or less. The magnetic field is pointing straight up between the rails. So if I look at the current here in my conducting movable projectile, then my current is going this way, my magnetic field is going straight up. So applying the right-hand rule, pointing my hand from the positive rail to the negative rail and curling my right fingers upwards in the direction of the magnetic field, I'm going to see that my thumb points forwards, or that's the direction of the force on this projectile. Since the current continues as the conducting projectile moves along the rails, of course that force will continue, so the projectile will continue to accelerate. As a result, you get a pretty effective sort of projectile launcher. Today's problem set, I think, is pretty quick, Tomorrow we'll look at one more consequence of the force on a current carrying wire in a magnetic field, and that of course is going to be how you create a motor.